Bismillahirrahmanirrahim. This is a report of the numerical analysis project. We will talk about one method for getting the positive root of the nonlinear equation, which is Newton-Raphson method, and two methods for solving the ordinary differential equation, which are Taylor series and Rangotta method. In the beginning, we have a brief introduction talking about the several benefits of the numerical analysis in our daily life. As we know, the nonlinear equation are the equation of order higher than 1. Usually these equations are very difficult to be solved analytically, so we use iterative methods as a numerical solution for this type of equations. This is Newton-Raphson method formula. Xn plus 1 equal xn minus f of xn over f dash of xn plus 1. Xn is the initial root of the equation, xn plus 1 is the next iteration root of the equation, f of xn is the nonlinear equation at the point xn, and f dash of xn is the derivative of the nonlinear equation at the point xn. Newton-Raphson formula is the most accurate iterative formula to get a positive root for a nonlinear equation. In question 1, f of x equal root 2x plus 1 minus root x plus 4 is a nonlinear equation that we are asked to solve using Newton-Raphson formula and x element to the interval from 2 to 4. Here is the MATLAB code for solving this problem, and here is the photos of the code and its output. We notice that the user is asked to enter the initial value of x and the number of iterations he wants to perform on the equation. The formula of Newton-Raphson is powerful as it finds the positive root performing a small number of iterations. The root of the equation of the problem is 3 as shown in the graphical solution of the problem. We can represent the MATLAB code using a flowchart, as it shows the logic of the code as a sequence of clear steps. Okay, what if we have a phenomenon in any field like science, economics, or engineering, and we want to make a mathematical model to convert it to a computer simulation of this phenomenon? The ordinary differential equation are the answer. We will solve the ordinary differential equations numerically. First, we have Taylor series, which expresses the function as the infinite sum of its derivatives, as we see in the formula below. In question 2, we are asked to find a solution for the given equation y dash equal xy to the correct 4 decimal places for the values of x from 0.1 to 0.5, given that y equals 0 at x equals 0. Here is the MATLAB code for solving this problem, and here is the photos of the code and its output. We notice that x increases the value of the function. We notice that as x increases, the value of the function decreases till it reaches 0 at infinity. And this is the flowchart representation of the MATLAB code for Taylor series. Rangotta is another method of solving ODEs. There are various orders of Rangotta method, but here we will discuss the third order only. Third order means that we have to calculate 3 intermediate terms, k1, k2, and k3, in every iteration we make. Then substitute with them in yn equation to get the y estimate for a given x. As the order of Rangotta increases, the accuracy of the estimate increases. Also, as the step size increases, the accuracy increases. In question 3, we are given a differential equation, y double dash plus y dash equal xy, and we are asked to get y dash and y double dash at x equal 0.1 and x equal 0.2. Given as initial conditions, y equal 1 at x equal 0, y dash equal 0 at x equal 1. We need to get the answer to the correct 4 decimal places using Rangotta's third order method. Here is the MATLAB code for solving this problem. And here is the photos of the code and its output. We notice that y is the corresponding estimate for each x and f is the derivative of y at the given x. The values of the first y and f are corresponding to x equals 0.1. The values of the second y and f are corresponding to x equals 0.2. And in the end, we have the flowchart representation of the MATLAB code for Rangotta third order method. Thank you for listening and goodbye.